All right, our next speaker is Andrew Schauer. Andrew works at the Chugach National Avalanche Forecast Center in Girdwood, Alaska. He's been forecasting for industrial operations and as a mechanized guide and also as an avalanche instructor. He's published avalanche research on lots of topics related to atmospheric sciences, geographic information systems, hazard mapping, risk communication, and also challenging forecast scenarios. He spends his summers in Montana and loves to sample the sweet British Columbia single track during biannual trans-Canada migrations between Montana and Alaska. We're fortunate to have two talks by Andrew today. The first one is going to be on deep slab avalanches and atmospheric circulations. Please welcome Andrew Schauer.
Thanks, Ethan. Yeah, thanks, Ethan, for that intro, and thanks to everyone who organizes this event. It's really fun to be a part of. Appreciate the opportunity to speak up here. This first talk that I'm going to give is presenting some work that I did as part of when I was in grad school at MSU a few years ago. And we were looking at the relationships between deep slab avalanches and large-scale atmospheric circulation patterns. I just really quickly would like to give a thank you to the people that helped me make this happen. So Carl Berkland, Jordy Hendricks, and Megan Higgs there were all on my committee and played a huge role in me being able to do this. And then Carrie Mock helped us publish a paper towards the end of it. We also received a research grant through A3, and then all of these avalanche centers and ski patrols on the lower right helped us with records and kind of refine the work that I was doing. Okay, so this framework of looking at these large-scale atmospheric patterns and relating them to phenomena that we see at the surface is nothing new. It's the field of synoptic climatology, and the idea is that those large-scale patterns are what drive weather that interacts with terrain, and then that's what makes these phenomena that we see on the surface. So in this case, we're looking at avalanches. You could do it looking at precip trends, snowfall, drought, wildfire behavior. It's a well-established field that has been applied to some avalanche work in the past, but this was the first time that we were looking specifically at deep slab avalanches. I'm going to talk a lot about 500 millibar heights. That was kind of the basis of what we were looking at to characterize these large-scale atmospheric patterns. There's probably a mix of people in the room that use these daily operationally and some that maybe have never thought about this at all before. But what we're looking at is a pressure surface that occurs between 16 and 20,000 feet above the ground. So we're in the free atmosphere where it has limited direct contact with terrain except for maybe some really isolated areas in North America. And it allows you to track air mass movement. You can look at areas where you'd expect to see subsidence or dry, warm descending air, or uplift where you'd see more unstable air masses, stormy weather. You can get an idea of what upper level winds are doing in terms of both direction and speed, and it allows you to start taking a first guess about some regional weather patterns that you might expect. There's some really simple features that you can tease out of a 500 millibar chart. So some things that we're looking for are troughs, which is where you see, these are called isobars. You can think of this as like a topo map. So where you see these dipping down to the south, that's going to be areas of generally lower pressure where you'd expect to see some uplift, unstable weather. You might also look for ridges where you'd see this tends to be warm and dry. And then you can also infer wind direction up at the upper levels here. The wind is going to travel parallel to all these bars. And then the tighter the bars are spaced, the faster the winds are going to be generally. So these are some of the features that we're looking for when we're looking at 500 millibar charts. So what we did for this work was we went back and got daily 500 millibar charts going all the way back into the 70s. And we ended up with something just under 6,000 days of data to work with. And the first step that I wanted to do was to say, okay, what are the main patterns that we tend to see over North America during the winter? And there's sort of two different ways where you can do a synoptic climatology study, and one of them is to start with the atmosphere, group similar patterns together and see what happens at the surface. You could also do that in reverse and look for similar days at the surface and then see what's going on in the atmosphere. So this framework that we did has been well established. We used a machine learning tool called self-organizing maps, which is really cool. Well, I'm a nerd, so I think it's really cool. But basically, there's two steps. First, it considers your entire data set as a whole. So in this case, it's just under 6,000 days of these weather patterns. And it analyzes and figures out the variability across the entire data set. So like what's any kind of pattern, atmospheric pattern that you might see over the past 40 years. Then the next thing it does is it assigns each day to a group so that similar days will belong to the same group. So, if you just look at this pattern in the upper left, there's somewhere around 1 to 200 days that looked something like this. And it combines similar days into one group, and then it arranges all of the groups in this two-dimensional array in a way that patterns or groups that are right next to each other will look somewhat similar, and groups that are really far apart will look entirely different. So it just is a really useful way to manage a large data set and start to look for patterns, because that's really all this is just a big exercise in pattern recognition. So these are the 20 types that I came up with using these self-organizing maps. There's no rule that says you had to use 20 types. I went through kind of rigorous method to settle on that number. If anyone's interested, we can talk about it, but could have been 10, could have been 50. We ended up with 20, and there's some really interesting patterns that pop out right away. So as you move from left to right across the array, you'll notice this ridge, which on the left side kind of occurs over the Pacific Ocean, migrates over towards the Intermountain West, and then it evolves into a trough as it's doing that too. So it's two very different setups there on opposite sides of the array. The other thing that we see is a transition from meridional or blocking patterns, which all that means is there's a lot of north-south movement here. These tend to be, you'll see less precip, like with a big blocking ridge over the continental U.S., than you would with these more zonal patterns down at the bottom, which is more enhanced direct west to east flow, more efficient vapor transport from the ocean into the mountains. And then the third thing that gets teased out here, which maybe we might hear a little bit more about with Kyle Mosley's talk later, but there's a teleconnection pattern, which is one of these synoptic scale weather patterns that is a recurring pattern. It's well documented, called the Pacific North American pattern. And that's a really big driver of precip over the Intermountain West. And we transition from a negative phase in the bottom left. As you move diagonally to the upper right, you end up in the positive phase of that pattern. And this is all just the computer doing that. So it's kind of cool, like it's pulled out these real world trends. There's other methods you can use to group these synoptic types together, but this one has been proven to pull out patterns that are real, and it worked really well in this case. Okay, so now that we've got those patterns characterized, we can start to do some kind of interesting things and start to tease out what we see at the surface for each pattern. So we looked at 3 study sites, Bridger Bowl, Jackson Hole, and Mammoth Mountain. I'll talk about what we found at Bridger, and just kind of keep in mind, any location with weather and avalanche records can do this exact same thing. We'll use Bridger Bowl as an example. So the first thing I looked at was what are the patterns that are big storm producers? And it did a really good job of documenting these sort of anecdotal things that we hear from professionals that have been working there for years or decades, or even just skiers that pay close attention to the weather. But our biggest storm producers are either when Bridger Bowl, which is the northernmost black dot here in our map, is situated on the downstream end of this ridge, so we're getting a northwest flow pattern. It tracks moisture right up the Columbia River drainage, so there's very little orographic barriers between the ocean and our study site. And then it also, when it hits the Bridger Ridgeline, it's the local terrain is oriented really well to kind of suck as much moisture out of there as it can. So we see a combination of those northwest flow patterns and then one that's more of a zonal pattern, which is, as I mentioned earlier, just is a really efficient way to move moisture inland from the coast. So these are the patterns where we'll see the most stormy weather. You can do the same thing, to compare the wet patterns versus the dry patterns, and looking at, for our driest days, we're looking up the top of the array, so more of those blocking patterns. And in the upper right, where we're in the positive phase of that Pacific North American teleconnection, and there's a ridge situated directly overhead, so warmer, drier. We also can look at temperature, what patterns are warm versus which ones are cold. And this is really cool how it just separates, basically, you can almost draw a line right down the middle of the array, and everything that's on the left side tends to be colder, and the patterns on the right tend to be warmer. So you can start to pull out some of what we're seeing at the surface over and over again over the 40-year study period here. And then if you take it a step further, you can say, okay, what's going on? We can show this interaction between the upper atmosphere and weather stations at the surface. How's that driving stability then over the course of a season? So we kind of separated the years into two groups, and we looked at the seasons that had a lot of deep slab activity and compared them against the seasons that didn't have hardly any, and pulled out some pretty interesting trends. So maybe the most notable is if you look at November through January, for our most problematic deep slab years, we see this really high number of these blocking patterns early in the season. And what that means is we're going to have lower precip, which is going to drive faceting and depth hoar development early in the year that could come back to bite us later in the year. The other kind of interesting thing was that during the same time period for these big deep slab years, we didn't see either of these patterns hardly at all, compared to like the whole study period where they occurred just as regularly as anything else. If you just pulled out the big deep slab years, they hardly ever occurred. So they're not the biggest storm producers. They bring some snow, but it was just kind of an interesting thing that stood out right away. It was like, hey, for whatever reason, during these deep slab seasons, we're not seeing that at all in the beginning of the year. And we did this for each of our 3 study areas. They each had different sort of preferences, and as a result, you'd see different concentrations, of different patterns during deep slab years. So these weren't necessarily the same patterns that showed up at Mammoth Mountain early in the year, but what was constant was that each site had some sort of higher concentration of patterns during the beginning of deep slab seasons than they did during an average or a stable year. So that was really interesting to see. Then the next thing we did was say, okay, what's going on right before we see big deep slab cycles? And it shifts, and instead of seeing that high number of blocking patterns, we shift to the bottom of the array. More zonal flow tends to be associated with loading events, pushing those deep layers closer, adding stress, and as a result, we see some avalanche activity. we broke them up into dry slabs and wet slabs, and maybe not a big surprise, during our wet slab events, we tend to see more of these warmer patterns than during our dry slab events. And again, each site had a different, they showed different synoptic types that were occurring prior to avalanche activity, but each one had like these preferential flows that were very commonly associated with big deep slab cycles. All right, so that's a lot of time to spend looking at weather charts and talking about weather patterns for a place that's about 750 miles from here. Why did I just waste all your time doing that? Well, there's a few take-homes that I was hoping to pass on here. One really valuable piece of all this is that it's a great way to objectively document these patterns and pass them on to new folks in your operation. So when I started working up in Girdwood, forecasting up there, I just took this same framework and pulled some records really quickly. I didn't go as in-depth, but I wanted to know what the weather does up there, and it gives you like a very quick snapshot with some really useful tools to identify patterns that could be, very useful at work. When I first showed this to the Bridger Bowl Ski Patrol when I was finishing up grad school, one of the guys was like, "Yeah, this is great. This is not anything we didn't already know." And I was like, "Well, that's kind of the point. Like, if I had pulled out all these weird patterns and started telling you guys that what you already knew was wrong, like, I probably would have blown it somewhere along the line." But what was different is that this is a really good way of like putting it down on paper and passing it to someone else, which if you were to learn it just on the job, that could take years to get that kind of experience. We've shown it as a framework for 3 locations in this study, but you can really apply it anywhere that has weather and avalanche records. The atmospheric stuff comes from a gridded data set that's available worldwide, so this tool can be used anywhere. And then the other cool thing, I didn't want to get too into the weeds about the machine learning part, but that's a really powerful tool that has not been used for the field of snow and avalanches all that much. There are a few other studies. It's been used as a forecasting aid. They've used it to characterize avalanche problem types. But I think there's a lot of usefulness. The way we were grouping circulation patterns together, you can use it to group demographics together. And that's, in the marketing world, they've done that quite a bit, where they're looking at like age, income level, geographic location. You could do the same thing with like experience, gender, education level, and look at accident statistics, for example. And really anything, like a lot of avalanche studies are in the business of grouping similar things together and looking for patterns. And this is a really useful tool that I think we've kind of like just started to scratch the surface with it. If you want to read more about this, we wrote a whole paper about it. It's a little bit dense, and I'm also happy to talk about it if anyone's got questions. If we have time for that.
Thanks, Andrew. Very interesting talk. And we do have time for some questions, so raise your hand and we'll get a mic over to you. We have one down here in the front. Mic's on its way. Thanks, Rich.
Thanks, Andrew. So, you're talking about using this technique in new areas and how you used it up in Girdwood, and I was just wondering, you've set up this really nice framework, and so if someone, at a ski area here in Colorado had, or a backcountry forecasting operation had an avalanche record for you to define their different seasons, like how much work would it take you to create like a similar sort of analysis given what you've already done for an operation?
Yeah, that's a good question. The biggest controlling factor will be the shape of the records. So if the records are usable and you can import them and pull out what you need right away, it wouldn't take much time at all. That classification scheme, you have one group designated to each day. If you have snowfall and avalanche occurrences for each day, you can do that really quickly. The problem is working with older records. Usually the most work comes to just translate those into something that you can put into a computer program and make them useful. So if the records are in good shape, you could do it in a few days. If it takes more time, it could take like half of a summer to put it together, something like that.
Right. So keep good records then.
Keep good records. Eat your vitamins.
Awesome.
Yeah.
Yeah, thanks for the plug for good data keeping. Here's another question up here. Wait for the mic, please. It's right there. Thanks.
So you arrived at the 20 kind of principal components. It feels like it's a principal component type of thing. That was based on like the machine learning variance, or are you trying to balance like the ability to actually interpret it? Like it feels like there would be value in 3x3 or lesser data sets that are easier to wrap your head around. Did you try to balance interpretation with statistics, or is it pretty, yeah?
Yeah, so you're right, like principal components analysis was, until pretty recently, was kind of the standard for doing a similar thing. Since it's shifted to this self-organizing map, but either way, you have to decide how many patterns you want to settle on. And one really common way to do that is you measure the amount of variability within each group, and you start with a small number of groups, so like a 3x3 array, I think was the smallest that we did, 9 types. And you measure the amount of variability within those groups, and then you start to increase that number, and you'll see this curve where that variability drops really quickly as you add more groups, and then eventually you're only getting incremental improvement as you continue adding. So we tried from 9 groups all the way up to 50, and there was somewhere between like 12 and 25 is where you started to see that curve flatten out. And at that point, it's just a decision that you have to make. And we could have done it with 12. I think you could have done it with 25. We could have done it with 50. But so we settled. It's somewhere in the middle of where you start to see like your reduced improvement as you keep adding, but hopefully like small enough where it's still usable and interpretable.
We have time for one more question. And, over here. Ron.
Thanks for that talk. It was awesome. A couple of things I've noticed, but one thing is you talked about early season and then 72 hours before the event. Did you look at those time frame, or you look actually at time series of how the weather develops throughout the season?
It was we just counted days, so I didn't look at all at like the evolution throughout the season. We pulled out those two windows based on previous research. Really, a lot of it was what Alex Marienthal had done, looking at where your best predictors of instability were to arrive at that 72-hour number. No, but I think it would be pretty interesting to see which patterns tend to occur in series, but we just never did that as part of this. Does that answer your question?
Yeah. Do I have another one?
Sorry, Ron. You can catch Andrew at the break. Thanks, Andrew.
Thanks.